My name is Michelle Thaller, and I am an astronomer. I work at NASA's Goddard Space Flight Center.
How astronomers seek to answer the biggest questions in the universe.
There's sort of two words that float about. There's astronomer and astrophysicist. And, it kind of depends on whether you're trying to put on a more friendly or formal vibe, I think. They really, these days, mean the same thing. I think there was a time when there was sort of a separation of duties. That there were people that, say, 100 years ago would map the stars and create all these wonderful catalogs of stars, and you might call those astronomers. The name is from astronomy, to name the stars. And then there were people that tried to figure out what the stars were and how they worked and what the science of it was, behind all that. Those would be the astrophysicists. And these days, the two studies are really the same. If you're an astronomer or an astrophysicist, you pretty much do the same thing these days. The word that was probably the best word, astrology, to study the stars, that one was already taken. A lot of the questions that I get from members of the public are these vast conjectural questions like, is there a multiverse, or what happened before the Big Bang? So for my doctorate, for my research, I studied binary stars. I studied two stars that orbit each other. And most stars in the universe are like that, by the way. And in the case of my stars, they had these wonderful colliding winds of high-energy particles that produced these giant shocks in the sky. The fun thing is that for a while at least, and maybe today, there are some stars in the sky that I've probably spent more time with than anybody else in the world. I observed them for hours and hours, trying to figure out how these colliding atmospheres worked. In the case of myself, I'm an observational astronomer. I went to observatories all over the world about 25 years ago when I was most active in research. I did a lot of research in Australia, in Arizona, the Kitt Peak telescopes, Mount Stromlo in Arizona. I also used a lot of satellite data. I had data from X-ray satellites and the Hubble Space Telescope. I actually got some time. You see, as an astronomer, you are allowed to write into these observatories. It usually happens once a year. And there is a panel that basically assesses what would all these people around the world like to do with the Hubble Space Telescope? And this panel of astronomers actually decides who should get priority. One of the things about being an astronomer is you end up doing a lot of writing. You end up doing a lot of writing asking for time on these telescopes and then hoping that your proposal gets selected. Another thing is you end up asking for a lot of time to write grants for money to support your work. If you get some time on the Hubble Space Telescope, often it comes with an amount of money to support the time you're going to do that research. So it turns out that being an astronomer, all of the training is about the math and the physics and the computer science. And then what you actually do day to day is often a lot of writing and a lot of trying to organize proposals and grants and how you're going to support yourself doing your science. And then if you work for a large organization like NASA, as some of your time as well is usually assigned to some specific mission, some specific space telescope, where you're going to be helping clean up the data, figure out how we're going to issue a call for proposals, organize the panels that are going to vet and look at all these different things. So in a way, you become kind of an administrator, a lot of meetings. I think that, the normal life cycle of an astronomer is probably 80% like business person. A lot of meetings, a lot of grants, a lot of budgets. But then, at least for me, there really was this time. It doesn't happen so much when you're a more mature astronomer, but when you're really young and out in the field and making your own discoveries, it really does feel like you're sort of alone with the night sky all by yourself up on top of that mountain. And you're seeing things coming down through your telescope that, it's a minor advance, but no human being has ever seen before. And it's a wonderful feeling of empowerment and sort of, kind of collaborating with the sky and seeing what we can figure out. One of the things is when you get a doctorate, you have to produce some kind of original research, something that's never really been done before. And that's not as hard as it sounds. That sounds very intimidating. I mean, how am I going to think of an idea that nobody's ever thought of before? But nothing in astronomy happens alone. What happens when you're a graduate student after college is you will join a professor doing his or her research with them, sort of as an apprentice. And then over time, as you get more familiar with the work, they will give you a little piece of that research, like, hey, you go ahead and take this part over yourself. You don't really need to think of things entirely just off the top of your head and come up with brilliant ideas out of nowhere. You start little by little working with a group of astronomers. And then slowly you start to ask your own questions. Maybe they've never had time on a telescope to look up this little bit of it, or this little bit of it over here is a new question nobody thought of. And eventually you realize that what you're doing is something that hasn't been done before. I guess there were probably about a dozen stars in the sky, but there were three that I really, really focused on. And in every case, these were binary stars. And these were stars that were very massive, stars that were, say, anywhere between like 15 and 50 times the mass of the sun, big stars. They actually only orbited around each other every couple of days, or at most about a week. So these are very big stars in very close orbits. And so it should make sense. These stars are pouring off not only light, but high energy particles, this wind of particles that we call stellar winds. And then they collide in between these two stars. Sometimes one of their winds will not be as strong as the other. So the wind from one sort of overtakes the other one and kind of blasts away the wind from the other one. And as they turn around each other, you actually sort of have this wonderful kind of three-dimensional view of how that shock wave goes all the way around. And so I use a technique called tomography, which is the same sort of thing you use in a CAT scan or something like an MRI, where you're trying to produce a three-dimensional scan of inside the human body. In this case, the instrument goes around you, but in the case of the stars would go around each other. And then I could use this sort of software mainly developed for medicine to actually try to figure out the structure of these shock waves. This is, just sort of workaday astronomy. Nothing, all that incredible or sexy about it, but it helps you understand stars better. It turns out that these shock waves are responsible for producing a lot of the molecules that we find in space. Stars create, atoms. They fuse hydrogen into helium, and then eventually helium into larger atoms over time. But these shock waves, at least in the cooler parts of them, can produce things like water, the water molecule. And there are some binary stars, like there are some in the Orion Nebula, that are producing enough water in a single day along these shock waves to fill the oceans of the Earth like 60 times over in a single day. Now, obviously, this isn't liquid water. This is water in a molecular form, a pretty hot gas, actually. But that's where a lot of the molecules responsible for life can come from, is from these shock waves. So it's a way of trying to figure out, just little by little, how the universe really does work, how stars work. So my research is much more observational, much more about stars. I certainly took classes in cosmology, the study of the universe as a whole. I took classes in quantum mechanics, graduate level quantum mechanics, graduate level electromagnetism, all of that. People often start right off with are there parallel universes? And I'd rather they sort of ask me, what are the importance of binary stars? There's honestly not all that many astronomers by number that do theoretical cosmology. Most of us are trying to figure out things like how stars are born and how they live their lives and die. We're trying to figure out what's left over after a star explodes, a black hole, a neutron star. Or we're trying to figure out how galaxies work, how many galaxies there are, how do we observe them, how do they change over time. There's only a few of us that are trying to answer questions like, what happened before the Big Bang, or, are there multiverses? We all study that to an extent. We all go to lectures at the conferences. I love going to the ones on, quantum theory and quantum gravity. Most astronomers study things that are a bit more concrete than that, if very far away. So it's often the case that, I'm giving some lecture on this wonderful new images of Saturn from one of our spacecraft like Cassini. And they're so beautiful, and we're learning things about the atmosphere, and look at these pictures of these little moons we took in the ring system, and we're studying the ring system, and we have a wonderful lecture. I turn to the audience and say, hey, any questions? And somebody raises their hand, and the first one is, are there multiple universes? It's like, Saturn. There are some words that are really easy to throw around, and in science they become interestingly complicated. People often say, do you believe such and such is true? Do you believe the Big Bang is true? Do you believe that the idea of multiple universes is true? A lot of these things. And when you're a scientist, you're aware that what you're doing is you're constantly trying to approach reality. You're trying to get closer and closer to describing something very well. But you're not all the way there yet. And it's quite possible that we never will be. It's quite possible that human beings with our limited senses and our limited brains even, won't really know what the true nature of reality is. It's one of these kind of wonderful things that, truth can change. 100 years ago, people were certain that the universe was not expanding, and of course we found out that it was. And you have to be able sometimes to take your very precious images, models of what the universe is like, about what reality is like, even about what the definition of truth is. You need to make sure that you're ready to change when better information comes on board. In physics, at least for the last hundred years, that has really challenged us to leave behind our human ideas of common sense, the very definition and perhaps existence of space and time. The whole idea about what is reality, what is existence, what am I, is a very, very complex question now to answer. I mean, to give you some ideas about this, there are some things that are very simple, like what is the interior of the sun like? It's obviously something we've never directly observed, but we see energy pouring out of the sun. There are actually waves, almost like earthquake waves that go around the sun that help us to study the interior, the way those waves travel. But do we know exactly how the core of the sun works? No, we don't. There are things that we get pretty close to, but we just don't really have the observational ability to do so. But then there are questions like, what are space and time, really? For so long, we've just sort of taken it for granted that space and time exist around us. Time flows in one direction, space extends perhaps to infinity. But then there was also a time when we didn't think that air was anything. People didn't realize that we actually live, at the bottom of this wonderful ocean of air that is our atmosphere. People took it for granted that air existed. That was actually proven in the 18th century, that this was actually something. Einstein showed us that space and time absolutely cannot be the simple way we perceive them. It all is related around the speed of light. The speed of light is always constant to any observer. One of the myths about Einstein was that he pulled all of these amazing ideas just kind of out of his head from nowhere, that he wasn't part of the scientific establishment. Well, in fact, he was. He was a professor. He was actually a graduate student trying to get a job when he was working at that patent office, that he had that miracle year where he came up with the theories of special and general relativity, among other things. So here's an example about allowing yourself to define whether something is true in kind of a bit more of an active way. Isaac Newton was able to describe very, very well how gravity worked. He was really one of the first people that said there's this force of gravity. And he just said that it's a force. This force permeates the universe, and this is why the planets orbit the sun. This is why apples fall from trees, is they're reacting to this force. And by using his equation of gravity, you could calculate that force very, very well. So you had this, great thing, the force of gravity. The force exists. It binds the universe together. But then you have to ask the question, okay, what do we mean by that? What is the force of gravity? What is it really? What causes it? And it took Albert Einstein to say that what we think of as gravity is actually a curvature of space and time. Things have to follow space and time. We are all embedded in the space and time of the universe. So if that space and time has a shape to it, a curve to it, we have to follow that. Light has to follow that. Light itself that has no mass can actually bend and go into a black hole. And that's because the light has to travel through space and time, and the space and time itself is bent. So all of a sudden, there was this answer. What is the force of gravity? It's a bending of space and time. So is that it? Is that the end of those questions that we can ask there? Well, how about the rather obvious next one? What is space and time? Okay, there's this thing that Einstein called spacetime, that space and time are sort of mixed together. They're two sides of the same coin. When you change one, the other has to change. If you are in a gravitational field and space is bent, time actually slows down. It actually affects time as well. We know that these two things are bound together, but what are they? Time can be different for different observers, depending on your velocity. If you're going very close to the speed of light, as people observe you going by, they see your time is very slowed down. If you're actually a photon going at the speed of light, time stops entirely. So what do we mean by this thing called time? And this is now what some of the major physicists of the world are grappling with, and they are trying to come up with some very interesting answers, and I think answers that will be very challenging for us. Imagine being a physicist back in the early 1900s and having this young Albert Einstein tell you space and time are bendable. You can change them. You can manipulate them. You might have thought they were crazy. How about looking at space and time instead as a consequence of quantum mechanics? A lot of people have been saying that relativity and quantum mechanics don't match. They don't work together. And this is true. This has been true since the beginning of relativity and quantum mechanics at about the same time. Relativity says that if you have a certain amount of mass, you can actually say space bends this much. And quantum mechanics says that everything is down to probabilities. The universe never has set answers, but maybe the probabilities of a particle being here versus there. Even the curvature of gravity must somehow be probabilistic. And Einstein didn't like that. There was no way to work that into his equations that actually made them both work at the same time. What if we were asking the wrong question? What if we're not looking at two different things? What if we could actually say that space-time itself is a consequence of quantum mechanics, not something separate from it, not two things that are clashing together? And this is the idea now that perhaps quantum entanglement, if you look at it correctly, is space-time. Now, quantum entanglement isn't just a term you can throw off very, very easily, but this is something that we have now observed and been able to replicate in laboratories all across the world, even in space, actually. If two objects interact together, they can actually sort of become, in a sense, the same system under the laws of quantum mechanics. So let me just give you a very simple example of this. A lot of people know the model of an atom where you have this nucleus of protons and neutrons, and the electrons can be in different orbits around there. In fact, in a single orbit around the nucleus, there can be two electrons. But those electrons can't be exactly the same. You can't have two that are identical. They have to have opposing spins, angular momentum. It turns out you can have two electrons in each one of these orbits, but the electrons can't be identical. They have to be spinning in opposite directions. It's a strange idea that electrons spin, but at least you can say that there's some kind of intrinsic angular momentum. What we think of as something spinning, that's actually a property that a particle can have, whether or not there's actually like a physical little ball. Electrons are not little balls, but they do have a property of spin, of angular momentum. You could have two of them in the same orbit as long as they have opposing spins, one spinning one way, the other one spinning the other way. So say that one is spinning up and one is spinning down, the way my thumbs are pointing. You know that these two electrons have to have different spins. So what happens if you actually take them out of that system? You take them away from the atom entirely, and now you've got these two little electrons somewhere in space. And you know that they have to have opposing spins because they once were in that same orbit. Well, okay, so now separate them. Separate them by a couple of feet, maybe a couple of miles. How about a couple hundreds of miles? Maybe there's no limit. We found out that if you use some sort of energy to change the spin of one of these electrons, the other one basically instantly knows that that's happened. And it's not that there is a signal passing between one of these to another, because it doesn't travel even at the speed of light. It is an instantaneous flip. It's not a signal traveling because these two things are basically the same quantum system. In the rules of quantum mechanics, they are the same object. So there's no signal really to travel. To a quantum system, there really isn't any such thing as space or time. It will adjust instantaneously because it's the same system, whether it's microscopic or whether it's many thousands of miles apart. They're the same thing. Could it be that everything is entangled to everything else in some way? Well, I mean, there once was a time when the universe was very small, the time right after the Big Bang, where in a way we were all kind of the same particle. That particle has changed and expanded, but is it possible to think that in some way we're actually the same quantum system to everything in the universe? And what we perceive of as space and time is the degree to which we're entangled. We're entangled more to things that are closer to us, that have a chance to interact with us, the air in this room, the space that's only outside in my yard. I'm less entangled to things that I've not been able to interact with much for a long time. Things like distant galaxies. I haven't been close to them since the beginning of the universe. Einstein asked, what is gravity really? And now we have to ask, what is space-time really? And we know it can't be as simple as the way we perceive it. Maybe the underlying quantum reality of the universe is that everything in a way really is still the same quantum system. I've always thought when people think about alien civilizations and they say flying saucers and UFOs and spaceships, I kind of wonder if the next step in really understanding reality is that there's no such thing as distance. And maybe a very advanced civilization that can somehow manipulate that. You don't have to travel anywhere in a spaceship. You simply figure out how you access this entanglement of the rest of the universe. Could it be that you are really the same quantum system as everything in the universe at once? And that degree of entanglement is what we think of as space, as time, as gravity. That's an amazing idea, and it's one that more and more people are starting to look at. Do we know this is true yet? No, this is still conjectural. But the physics is working very well. And one of the promising things is that the equations of gravity emerge now from quantum mechanics. They're no longer general relativity, quantum mechanics, they don't mix. You start with quantum mechanics and gravity emerges from it, from the degree of entanglement. So stay put for a couple more decades. And like I said, maybe someday we're actually going to figure out what the underlying structure of this entanglement is. And then we can actually move outside of space and time. When you are pure energy, you have to travel at the speed of light. A photon has to travel at the speed of light. It can't go any other speed. A photon can't exist in a state where it's only moving at, say, 20 miles an hour. It has to travel at the speed of light. And when you're traveling at the speed of light, you don't experience space or time. You're probably familiar with Einstein's idea that as you go faster and faster, closer to the speed of light, time slows down for you compared to an observer watching you. If I'm sitting here still on the Earth and I watch somebody in a spaceship whizzing by at half the speed of light, I see them very, very slowed down compared to me. And when you're actually going at the speed of light itself, time stops. That means that light does not experience space or time in any kind of extended way. All points in space are one, and all points in time are one. Time and space don't exist to a photon the way it does to us. And yet I am made of something that you can convert to photons and back and forth. And I experience space and time. I experience those as extended properties. There's a duality to the universe, and I think this is going to become one of the most important things for modern physics, that the next revolutions in physics. Light around us, I mean, it's coming from the sun through my windows, it's coming at me through, the lights that we have in the studio, doesn't experience the same universe I do. To it, in a real way, the universe never expanded. All points of time and space are still one from the perspective of a photon. And I am made of photons, kind of. But why do I experience space and time? Space and time as we perceive them cannot be the end story. There has to be a different perspective that shows us a reality that our human brains don't perceive yet. But the physics all around us of something as simple as light demands it. The things that kind of give me chills is just how little we understand the nature of a reality itself. If something bouncing off me right now doesn't experience the universe as having even expanded, what does that mean? So that equation, E equals mc squared, I mean, it's useful. You can use it to power nuclear reactions. You can use it for particle accelerators. But it actually sort of claws away the fabric of reality itself and challenges us to ask what's underneath. To me, I think one of the most amazing things about the universe is the question, what is energy? And this can go very, very deep. A lot of us are familiar with, energy it takes energy to accelerate something, like, to actually throw a softball. That takes, energy, chemical energy from your arms. Or you could say something has potential energy, like it's sitting at the top of a hill and it's prone to roll down the hill in the gravity field of the Earth. That's actually called potential energy. But then there's also the energy that's just intrinsic in matter. One of the things that always gets me about this is that energy, light, light is sort of a form of pure energy. And us, matter, we're made of particles like protons and neutrons and electrons. They seem so different. They seem to have completely different views of the universe as well, which I think is one of the more interesting and disturbing things I know about in modern physics. Let's just think about the idea that energy and mass really are somehow the same thing. That mass is some coagulated, stored form of energy. That means the two of them, you can actually go from energy to mass and back and forth. And that's the famous equation that Einstein came up with, E equals mc squared. That in any amount of mass, there is an equivalent amount of energy, and the two are basically the same things. The universe actually doesn't seem to see much difference between mass and energy. As long as the amount is the same, it can exist in either form. And let me give you some examples of that. The way a nuclear reaction works, like a nuclear fusion reaction, is you convert some amount of mass into pure energy. Nuclear fusion actually brings particles together, slams them into larger atoms, and in the process, energy is released. So a little bit of mass is lost, but energy is produced. It also goes the other way. In a particle accelerator, you get more and more energy because of collisions of particles colliding together. They produce so much energy that as long as a given particle has that amount of energy, any particle can pop out of that reactor. And that's how we find new particles. As we get to higher and higher energies in a particle accelerator, just having that amount of energy around The universe can manifest it now as mass. It takes a lot of energy, equals mc squared. Energy equals mass times the speed of light squared. That's a lot. But energy and mass pretty much are the same thing. One of the ways the universe seems to do this is something called virtual particles. That if you have, just the energy, around you, the energy of space and time itself, there's sort of an inherent energy just in the universe. That energy can actually become mass. It'll actually form what we call virtual particle pairs, like an electron and its antimatter equivalent, a positron. Those two particles will just literally pop out of the universe because there's that amount of energy around, and then pretty much always they just annihilate each other. They just go back. Matter and antimatter annihilate back into pure energy. And this is happening all around you. Everywhere around you in space, these little virtual particles are forming and collapsing together all the time. Some of the more interesting things happen in the universe when those particles get separated. One example is around a neutron star. It can actually make a beam of energy coming off the magnetic poles of the neutron stars by having virtual particles be created and then accelerated by the magnetic field. So all of a sudden you have this energy that wasn't there before, produced by the virtual particles themselves. As you get to higher energies, say you have a very, very strong magnetic field, very high energy. Again, we find these around neutron stars. That can start creating lots and lots of these virtual particle pairs. And the more energy you have, the more of these little virtual particles you get, until space itself takes on an aspect of having mass. The density of these virtual particles right around a neutron star, even in empty space itself, would be about 3 times the density of iron. It's just unbelievable. So energy and mass really are the same thing. They're two sides of the same coin. They can be converted back and forth to each other, and the universe doesn't really care. It sees them both the same way. When people think about the most dramatic things in space, they tend to go immediately to black holes, which are absolutely incredible. Out of control gravity that you can actually suck light back in. It's just amazing. But I think neutron stars deserve a little more love, because a neutron star is also created when a massive star dies, but it doesn't have quite enough mass to actually collapse into a black hole. It actually leaves behind a thing, a physical thing that you can study. So while black holes are this bottomless pit, with neutron stars, you have this very strange thing that you can look at them, you can observe them, you can take real measurements of, and you're looking at something that is mind-blowing, and in some ways our physics really isn't ready to describe yet. The thing about a neutron star, why do we call it a neutron star, for one thing? And I'm going to really oversimplify here, but basically, when you think about an atom, you have protons and neutrons in the nucleus of the atom, and then electrons are in orbitals farther away, around the nucleus. Amazingly, the gravity of a neutron star is so strong that it actually collapses the electrons into the nucleus. The gravity crushes electrons into the nucleus. And if you crush an electron and a proton together, one is negatively charged, one is positively charged, you will get a neutron. A neutron actually will naturally decay sometimes into an electron and a proton. You have an object that's mainly made of neutrons. There are some protons as well. And it basically has the density of an atomic nucleus. But it's about 10 miles across. That's like one big nucleus, 10 miles across. That's incredible. And because there was so much collapse involved in their forming, when you think about what they call the conservation of angular momentum, if something is spinning, and stars actually do spin, if you collapse that down, you actually spin up much faster. It's the classic ice skater analogy. You have an ice skater with her arms out spinning around, and then as she draws them in, you can watch that ice skater spin faster and faster. Same thing happens. But in this case, you actually have a ball that is about 10 miles across, spinning 500 times a second. That in itself is just mind-blowing to think of, right? Something that big spinning that fast. Now, recently, neutron stars have played this important role in explaining something that we had no explanation for. They were very, very mysterious. In fact, there were some people that were wondering if we were actually looking at might be a signal from an advanced alien civilization. Those are called fast radio bursts. Now, fast radio bursts have been in the news for a couple of years because there was so much energy in these mysterious bursts of radio emission that we couldn't explain what was going on. So, for example, we would have, our radio telescopes would register a burst of emission, and that burst would last, say, a millisecond, 1,000th of a second. That's about how long these things would last. But in that 1,000th of a second, enough energy was radiated similar to what the sun puts out in a week, in a millisecond. And so we were getting these signals from, all over the sky. And we were trying to figure out what that could possibly be. How could you make that much of a tight burst of radiation in that small amount of time at those incredibly high energies? So the race was on to try to figure out what these fast radio bursts really were. Luckily, we have many, many things that are at our disposal to try to study these things. Right now, we have many high-energy telescopes that actually are orbiting the Earth that measure things like X-rays and gamma rays, the most energetic types of light. Light you only get if something is in the millions or billions of degrees. It'll actually emit X-rays and gamma rays. A wonderful thing is that we actually started to be able to kind of pinpoint where these things were coming from in the sky. And as we did that, they actually seemed to line up with neutron stars. So neutron stars are most likely responsible for these fast radio bursts. Now, exactly what's happening is something that we don't really know yet, but it probably has something to do with almost like an earthquake. An earthquake, you have something, something in our crust shifts, and there are all these waves that go through the Earth. It's actually the way that we know the interior of the Earth is by studying those waves. We've never been able to actually take a sample of the fact that the Earth has magma all the way down until you get to at first a liquid metal core, then a solid metal core. No one's ever seen that physically, but we actually watch how these waves of compression go through the Earth, and we can put together what the interior of the Earth must be like. The same thing may be possible for neutron stars, but on a much more energetic scale. You have this ball of neutrons, incredible densities, incredible temperatures. And we think that there must be a crust of neutrons, that actually forms on the outside of these stars. And inside is probably a fluid of pure neutrons. We know this because neutron stars, as they spin, sometimes seem to sort of slosh around, almost like a water balloon. So we've modeled that to be sort of a crystalline thin crust. I can't imagine what that would be like. For one thing, the gravity would be so intense near that crust that it would just crush you into just particles, basically, on the surface of that neutron star. But if that crust were to have a flaw in it, and there was some sort of, a quake, it shifted somehow, it would send compression waves through the neutron star and release tremendous amounts of energy in a quick little moment of the crust actually sort of refiguring itself. So right now, our best explanation is that these amazingly mysterious fast radio bursts are probably neutron star quakes. And just like earthquakes have taught us so much about the interior of the Earth, now we're looking at the signal, even in a thousandth of a second. Take that signal, pull it apart, and try to find the structure that's going on inside that burst of radiation, and see if we can reconstruct what the inside of a neutron star is like. Neutron stars really are these real monsters. Unlike black holes, you can see them. You can see their surfaces. You can actually map how the radiation is coming off them. When it comes to really mysterious parts of the universe, but things that you actually can measure, I'd say go for some neutron stars. The closest neutron stars to us are very far away. They're on the order of many hundreds or thousands of light years. So luckily, they don't really cause any trouble for us. But the question I've always wondered is how close could you actually get to one of these things and make a measurement before you would just be fried by radiation? Or in the case of a neutron star, something stranger still. A lot of people are familiar with Einstein's famous equation E = mc squared, which says that energy is equal to mass times the speed of light squared. And what that really means is that in any amount of mass, so if I think about like the mass of my little finger, there's a tremendous amount of energy. So if I could convert my little finger into pure energy, the nuclear bombs that were dropped on Japan, converted on the order of like a dime's worth of mass. So, there would be many, many nuclear warheads right in my little finger's worth of energy. But E = mc squared also goes the other way. If you have a lot of energy, that basically starts acting the same way as mass. And it does so in something called virtual particles. If you have a lot of energy in a small space, the universe will start to actually create particles that have the same energy in their mass. So a lot of energy can actually become mass. And this is how our particle accelerators work. This is why you can discover new particles. Because if you just have a very energetic collision, like you take two gold nuclei and you slam them together, there's so much energy produced in that collision that it starts to pop off particles just from the amount of energy. And as long as you have enough energy, you can make any particle the universe has. The particles come off in all different flavors as long as they have the same amount of energy that collision is putting out. So neutron stars are doing something kind of like that. They're actually becoming sort of natural particle accelerators in a way just because of their mass. There is so much gravitational contraction that the magnetic field, the electric field and magnetic field of that star is actually compressed around this tiny little object now. So neutron stars have magnetic fields that are trillions of times more strong than a typical magnet you might have in your home, like a refrigerator magnet. It would actually pull regular matter apart, just the magnetic field. But there's so much energy in those magnetic fields. So think about E equals mc squared. There's so much magnetic energy right around a neutron star that the vacuum of space itself starts to make these virtual particles. And I was at a lecture one time, and this just blew my mind. This is what happens when you work at NASA, and you go into a lecture your colleagues are having, any day of the week. And they were saying that right around a neutron star, the density of space itself, the vacuum of space, right, a place where it's a vacuum, there aren't any particles otherwise, has about 3 times the density of pure iron. Just from that amount of virtual particles being produced by the energy of that magnetic field. So what's it like to fly around something where space itself has the density of 3 times of iron? What's that like? What does that look like? I would love to see what a neutron star looks like from a safe distance, and I'm not exactly sure what that is. When you're dealing with so much energy that even empty space becomes much more dense than iron. And once again, these are real. They're up in the night sky tonight. I mean, you can't see them because they're dim and they're small and they're far away. So it's not something we actually see in the night sky. But all around us, we're getting the radiation, the high energy radiation from these things that are real monsters. Our sun has this wind of high energy particles. This is something that was only relatively recently discovered. I mean, when you think about the fact that the very first satellites we put into space, starting in the very late 1950s, and 1960s, they realized that there was this source of radiation up there. There was a lot of particles around up in space. I actually had the honor of being next to this man named Eugene Parker. We have a wonderful mission named after him called the Parker Solar Probe. This mission is actually orbiting around the sun right now, closer than any human-made thing has ever orbited the sun before. It's really, really exciting. He was, I believe, 94 years old at the time of the launch. Usually, we only name spacecraft after people posthumously, after they've died. He was the one that basically predicted the solar wind and was the one that figured out how it worked. And of course, we're still figuring out a lot of the details. But they just couldn't think of anybody better to name it after than him. And so that was lovely. The source of these high energy particles and exactly how they get accelerated away from the sun is what we're studying right now. We know that this wind of particles, when I say high energy particles, I'm talking electrons and protons and sometimes as large as like the nucleus of a helium atom, something like that. And they get blasted through our solar system at 1 million miles an hour in some cases. And so, we have this very high energy wind. It changes planets. It's responsible for Mars losing its atmosphere over time and becoming this kind of cold, dead desert. It's responsible for Venus becoming sort of this hellish thing that we know it. It actually blasted away all of the lighter molecules like water. And it left Venus with an atmosphere of carbon dioxide and sulfuric acid. And even Pluto, all the way out at the edge of our planetary system, Pluto is still losing tons of atmosphere a day, blasted away by this wind of high energy particles. The only reason the Earth is not really affected by it much is because we have a very strong magnetic field. And so, our molten metal core, all that molten metal moving around inside the Earth generates kind of a magnetic bottle around the Earth, and that protects us from the solar wind. But someday, the sun will actually, pretty much blast away our atmosphere anyway. So, planets change. And one of the important things about knowing about this wind is we have to understand our environment in space. The solar wind normally is at levels that humans can take quite easily. I know that some people that are into conspiracy theories say, how could we have gone to the moon because there's so much radiation in space? Well, the answer is we kind of got lucky with Apollo because a normal day, the solar wind is a radiation level humans can handle quite easily, up in space or on the moon. Problem is that if you have a solar storm, a very, very violent event that unleashes lots of this solar wind, A lot of times we call these coronal mass ejections. The corona is the outer layer of the sun's atmosphere. And coronal mass ejection, all this stuff comes out at once. It's true that if a big one of those happens in the direction where astronauts are, unprotected from the Earth's magnetic field, they could die. I mean, it could actually give them a fatal dose of radiation. That is something that we need to consider. And it turns out that we got kind of lucky that, in between some of the Apollo missions, when no astronauts were up on the moon, luckily, we actually had events, solar events that would have endangered the astronauts. That's why it's hard to go to the moon and also to Mars, is to protect people from that radiation. It's not that hard to protect you from it. I mean, a good amount of water could do it. Like if you had a water tank in your spacecraft and you could shelter behind that. It's just that you'd have to bring up a decent amount of water, and that's a lot of mass. Or in the case of the moon, I think if you could dig down just about 10 feet below the lunar surface, that amount of rock above you would shelter you. But then we need to bring, construction equipment to the moon that can dig a tunnel, right? So, I mean, there's all kinds of things we're considering as to how you would handle that. So what happens with shock waves is that you have, say, two binary stars close to each other, and they both have a wind of particles. In this case, we don't say a solar wind, we say a stellar wind, because we're talking about stars, but it's really the same thing. The main difference is that the stars that I was studying are very massive stars that have, anywhere from, let's say 20 to 50 times the mass of the sun. And they actually have really strong winds, much stronger even than the sun does. So when you have these two stars close to each other, these winds come off and they collide. And when that happens, I mean, literally the electric and magnetic fields, sort of entangle with each other, the particles collide together, and that creates a very, very hot area that we call a shock wave. As all of this stuff comes together, basically slows itself down as it collides, you get all of this heat and radiation emitted along that shock front. Those are wonderful shock waves that are created by colliding winds. Yeah. So one of the big challenges right now, especially as we consider putting astronauts back on the moon, is there a way to predict when one of these violent events is coming? The answer is yes, in several ways. So in the very simplest way, we actually have spacecraft. As I mentioned, there's a spacecraft orbiting the sun right now. There's actually two, the Parker Solar Probe and the Solar Orbiter from the Europeans. And we also have other spacecraft between the Earth and the sun. As one of these big belches of material, charged high-energy particles, comes out of the sun, it will hit different satellites that will measure how fast it's going, how much energy is being delivered. And usually in the case of say, the moon, the Earth has about a day or maybe 2 days notice. So you could say to the astronauts, hey, something's coming, everybody go shelter, as long as you had a good shelter there. But then there's the question of, can you predict it before it actually happens? And this, of course, is one of the huge goals all over the world of people called heliophysicists. Helio for sun, and then physicists. So people who are physicists that specifically study the sun. The sun is this incredible magnetic marvel. A magnetic field is generated by moving charges, right? So you think about like the charges in moving metal that generates a magnetic field in an engine. In the case of the sun is made almost entirely of hydrogen. But it is so hot on the surface that gas has become ionized. Now, what that means is there's so much energy that electrons that normally orbit around a nucleus, the electron gets so much energy it just takes off. And that leaves two particles that are charged, an electron and a proton. Anything that has an electric charge, a magnetic field can bend. And so when you see these wonderful like loops on the sun and all of these beautiful shapes, that's the very hot electrically charged gas just following the magnetic field of the sun. The name for it, and it's kind of a confusing name, is plasma. You could actually see the shape of the sun's magnetic field, but it's chaotic. It's incredibly complicated. So you have these wonderful loops of magnetic energy, all this stuff following it. So how do you predict, when one of those loops is going to break open and actually like spew stuff out and create one of these big ejections? We're getting better at it, but it's still something that we don't understand. I mean something that's simple about our own star. When is there going to be a really big storm? We can't predict it down to the hour. We can say there's a very active region here that looks like it might produce something, but there's no way to guarantee that. Actually, it kind of reminds me of the year 2012. Because I was having sort of a difficult year that year because people had this idea of the Mayan apocalypse. It was 2012. Apparently that was the end of some calendar cycle in the Mayan calendar. The idea was that something catastrophic was going to happen. And I would get calls. Seriously, people would call us at NASA and say, I don't want my pets to suffer. Should I euthanize? I actually got a call, somebody wondering if they should euthanize their pets. Other people would say things like, is the world going to end next month? And I'd say, look, okay, if I knew the world was going to end next month, do you think I'd be here in my office answering phone calls? I don't think so. And we kept telling people that there was really no reason to worry about anything. There was nothing unusual astronomically happening. The sun was in a naturally active period that year. Every 11 years or so, the sun becomes very active, and then it kind of gets quieter again. One of the reasons I know this is because I love to see the northern lights, the auroras. Those are caused when you get these charged particles in our atmosphere, and they create these beautiful glows around the poles. For us, that's really the only thing we really notice for the most part. What happened actually is that there was a colossal coronal mass ejection, one that would have actually been dangerous to our power grids here on Earth. It wouldn't have caused any damage to people or animals or plants, but it would have actually dumped electric current into our magnetic field. And it probably would have taken down, a lot of power grids. It would have caused a lot of damage. The thing, though, is it went off on the other side of the sun from the Earth. And we had satellites out there in that other direction, out in the solar system, and they got knocked silly by this big burst of charged particles from the sun. And so we looked at that, and we were able to observe it and see what had happened and track it and all of that. We all kind of went, phew. The sun spins. It actually doesn't all spin at the same rate. The equator spins faster than the poles. It's not a solid thing. It kind of twists itself up. The sun, on average, spins about once every 29 days. And so we don't really know. There could be an active region that's about to blast, but then it could spin out of our view, and so we're safe from it. Or something could come, from the other side of the sun that we didn't see. There's all sorts of wonderful complexities when it comes to observing this phenomena we call space weather. The winds and the storms, but in this case, winds of particles and magnetic storms of magnetic chaos on the sun. It's a wonderful thing to think about that our lovely, gentle star up there is actually very dramatic and very volatile. Sitting here at the bottom of the Earth's atmosphere, we're not really aware that we're in a larger environment in space. And the dominant thing is the sun. The sun obviously is the biggest thing in our solar system, the most important thing. The sun not only puts out a lot of light and heat, but it also puts out a wind of high-energy particles, high-energy protons and electrons, charged particles. We actually are bathed in this all the time. It interacts with our atmosphere. It creates the northern and southern lights. In some cases, it can even be a risk, especially to our technology. We're quite well protected from these high-energy particles by our atmosphere and also by the Earth's magnetic field. The Earth has a very strong magnetic field that surrounds our planet and protects us from the worst of this stuff. Even the astronauts up in the space station, they're actually close enough to the Earth that they're largely protected by this magnetic field. When you go out to the moon and farther away, that's when you're not protected by the Earth's magnetic field. And you find yourself just basically exposed to this wind of high-energy particles. A lot of people don't realize how significant that is and how much not only NASA, but NOAA and other organizations all over the planet are monitoring this. There is a fleet of satellites right now, and I don't know exactly the number because it usually changes, but we have some satellites that are orbiting the sun itself. We have some that are actually placed between the Earth and the sun. There is a place that actually the sun's gravity and the Earth's gravity balances out. If you're between the Earth and the sun, you're actually attracted equally to either one gravitationally, and you stick a satellite right there, and it doesn't take a lot of energy to actually keep it in that spot. So we have this kind of early warning system to see if there's something dangerous coming from the sun. And then we have all kinds of observatories, both here on the Earth, on the ground, and also space-based observatories that orbit the Earth that just look at the sun continuously. We even have satellites around the solar system to look at different angles of the sun. So we've got the sun covered. Now, why is it so important? Well, the solar wind normally doesn't really have much danger to us, or the environment in space. But when you're dealing with space weather, sometimes there's a really big line of thunderstorms coming through, right? So in the case of the sun sometimes has very, very violent storms. And these are storms caused by the chaotic, twisting magnetic field of the sun. Some of the hot gas on the surface of the sun actually gets accelerated so quickly by these magnetic fields that it just breaks off and takes off into space. And in one moment, you could have trillions of tons of fast, high-moving, charged material coming out towards the Earth. Now, that's not actually very dangerous to us biologically, but what that can do is carry a huge amount of electrical and magnetic energy. All of a sudden, all these charged particles hit the magnetic field of the Earth, and they can actually dump electric current right into our magnetic field. There was a famous event in the mid-1800s called the Carrington event. With the Carrington event, we really were just starting to have things like telegraph lines. Now, in order to get a telegraph to work, there has to be electric current on the wires. And normally you would hook up your telegraph to a power generator, and that would create electric current and you could send your signals. So when this Carrington event occurred, there was so much electric current dumped into the Earth's field that you could actually start sending signals with no connection to power. And then eventually, as the storm went on, some of the telegraph wires actually caught on fire just from a storm of magnetic and electrical energy, these particles coming from the sun. So these days, of course, we know that this could happen again. Events like this are rare, but they certainly will happen from time to time. So there are all kinds of organizations, like FEMA, all these disaster relief organizations that work with NASA and NOAA to actually figure out what happens if we think that a dangerous solar storm is imminent. In the case of all of our satellites up above the atmosphere, they're very at risk. So we can basically shut them down, put them to sleep for a little while. Of course, that energy burst will hit them, and it may damage their detectors, but at least most of the electronics are shut down at the time, and we can recover them, hopefully. And then there may even be plans that are necessary to shut down parts of power grids. Because I think the biggest danger of these things to us is that when they actually hit the Earth's field, you could have so much, again, energy in that magnetic field of the Earth that it could fry our power grids. I mean, think about how bad it would be if all the power on Earth just went out because of one of these solar storms. I mean, that could conceivably cause billions or maybe even trillions of dollars of damage. So there are people rehearsing these scenarios. There are people trying to figure out how we would shut things down, how we would protect ourselves. And then we have our fleet of satellites trying to observe the sun all the time. And we would have probably about a day's notice as one of these big storms made its way through the sun. The sun we think of as putting off lots of light, and light travels at the speed of light, which takes about 8 minutes to get from the sun to us. But this isn't light. These are charged particles, protons and electrons. And although they may be moving millions of miles an hour, it still will take them about a day or more to get to the Earth. So we will have some warning. But yes, I mean, all around you, there are people monitoring space weather and getting ready for a big storm. The thing that's really fascinating to me about asteroids is that they are kind of a preservation of the way the solar system was billions of years ago. This is really true. The solar system was once this kind of cloud of gas and dust. And then under the forces of gravity, things started to clump together into smaller bits and then larger bits that eventually became planets. And planets like the Earth change so much, right? I mean, the interior of our planet is molten. There's stuff that's melting down there. On the surface, you've got erosion and rain and wind. So nothing is really the same as it was billions of years ago. But there were these little small building blocks that got left behind that actually never got made into larger things, and they're pretty much unchanged for billions of years. So scientifically, the reason these are such treasures is that they are kind of a time capsule of what the chemistry, the physical conditions, everything was like as the solar system formed. The question of mining them. So the thing that happened with the Earth is that the Earth has this hot molten core, and most of anything that's heavy sinks to the bottom, right? So when you have a liquid, heavier stuff sinks to the bottom. So the core of our planet is made of iron, and nickel, but also metals like gold and silver and platinum. Anything that was heavy when the Earth was molten would have mainly sunk to the core. So that means that if that didn't happen to an asteroid is still kind of all mixed up. The heavier stuff hasn't actually sunk out of it. Given a volume, there is in fact more rare elements, more gold, more platinum, more titanium, whatever. But asteroids are also fairly small, and of course they're in space, so they're hard to get to. To me, it becomes kind of a cost question. Yes, asteroid material, by and large, has more rare, valuable elements than parts of our Earth's crust. It also has a lot more iron. You can get very expensive iron. I don't know when it will actually become economically feasible to go all the way to an asteroid, mine it, bring stuff back, or however you want to do that, to get the tiny little bit of gold that you'll get out of it. My guess is not soon. I don't think we will actually be mining asteroids in any real commercial way very soon at all. It's a fascinating question whether you could use a compass in space. So Let's talk first about compasses, and then maybe talk a bit more about the idea of how we locate ourselves in space in general. A compass is something that responds to a magnetic field. So the reason a compass always points north is that it's responding to the magnetic field of the Earth. Our planet has this wonderful core of molten metal. That metal moves around inside the Earth and it generates a magnetic field that has two poles, a north pole and a south pole. When you make a compass, you make it out of something metal that can respond to that magnetic field, and it points to the magnetic pole of the Earth, which is very close to our north pole. A magnetic field directs compasses. Obviously, if you go away from the Earth, far away from our planet, it's no longer going to be able to feel our magnetic field. So a compass will not point to the north pole of the Earth if, say, you're out by Saturn. Saturn and Jupiter are separate planets, and they have magnetic fields of their own. So certainly, if you were actually close to Jupiter, Jupiter has a magnetic field much stronger than the Earth's magnetic field. Your compass would definitely point to the north pole of Jupiter if you were actually around Jupiter now. But what if you get farther out? What if you actually go farther from there? Is there any magnetic field out in space itself? Well, actually, it turns out that that our galaxy does have a magnetic field as a whole, too. This magnetic field might be hard to detect. You might need a very, very sensitive compass, but say you had it, you would actually see that our galaxy does have sort of a magnetic north and south pole, and that magnetic field permeates our whole galaxy. With compasses, you could actually at least find out where the north and south pole of another planet is, the north and south pole of a star. A star has a magnetic field too. Even the north and south pole of a galaxy. That's responding to a local magnetic field. But then it kind of begs the question, how do you find your direction in space that doesn't involve a magnetic field, out between the galaxies, where really there's no detectable magnetic field at all? Everything is moving. There's nothing to say, this point is still, and this is the reference point we're going to use, and everything moves according to that point. We're moving around the sun at about 66,000 miles an hour right now. The sun is moving around the galaxy, around the core of the galaxy at about 500,000 miles an hour. We are actually falling gravitationally into the center of a cluster of galaxies at about 1.5 million miles an hour. That's just when we say relative to what? Relative to the sun, relative to this group of galaxies. There is no absolute standard of reference in the universe. There is one thing that is perhaps the best way of navigating your way around the universe, and that's something called the microwave background radiation. That's the farthest radiation we can possibly see. That's radiation that's coming everywhere in the universe from a time about 400,000 years after the Big Bang. And it fills all of space with this gentle microwave radiation. And it's pretty much the same in every direction. In fact, if you had an old-style television that used to have an antenna decades ago, a lot of the static that you would see on the screen was actually microwaves from this background radiation. And one of the things we can measure is our motion relative to this bath of radiation, the microwave background. So if you were trying to navigate with a compass in space, just remember that compass is going to respond to the strongest and closest magnetic field. It will point north, north to the pole of a planet, north to the pole of a star, even to the north and south magnetic poles of our galaxy. But what you're reading is a magnetic field. That's what a compass does. And that's pretty much all it can tell you. Well, this is the thing about the power of astronomy that kind of really does blow my mind, is how much we actually do know. There's all kinds of things that we don't know. And astronomers, scientists in general, tend to really focus on what we don't know because that's what we're working on. That's our jobs. that's how we get, the grant money to sustain ourselves, is trying to answer the questions that we don't know yet. But the things that we do know, in some ways, just how recently we know them, really kind of blow my mind. You think about, what are stars made of, right? I mean, you've probably heard that stars are mainly made of hydrogen and helium. They're these big sort of balls of gas, very, very hot, dense, burning balls of gas. But how long ago did we know that? It was actually really not until, times like the 20s or 30s that a young woman named Cecilia Payne, working at Harvard, wrote a PhD dissertation pretty much proving they had to be made out of hydrogen. It was a graduate student, a woman graduate student. At the time, the idea was that the sun was probably something very much like the Earth. It was like a big rock. And if you have a rock that big, and this is true, there would be so much gravity pushing it together that the temperature of the rock would be very hot. So, the temperature of the surface of the sun is round about 10,000 degrees. And if you had a rock that big with that much gravity pushing it together, it would be that hot. But it would only be that hot for probably a couple million years. And the neat thing was, around about the late 1800s, it was Charles Darwin who had been looking at things like evolution, the strata of rock like the Grand Canyon. And he sort of had this feeling that millions of years certainly was a long amount of time, but he didn't think it was long enough for the changes that he saw in the Earth itself. The prevailing idea, and this was a problem, is that the sun was basically a big Earth. Gravity, just the contraction of gravity was making it hot. It would take millions of years to cool off. It turns out that wasn't it at all. It was actually made of hydrogen, the lightest substance in the universe. But now you have so much gravity crushing together the hydrogen, making the interior very hot, millions of degrees hot enough actually to start a nuclear fusion reaction. And that can last billions of years. Certainly one of the biggest misconceptions is that people think that scientists feel that the Big Bang came out of nothing, right? I mean, how did all of this energy and all of this matter that made up the universe, you're saying it just came out of nothing? No, I don't think any scientist actually believes that. The problem is, when you think about the condition the universe was in at that point, where, take our observable universe, right? You can look from one side of the universe to the other, back 13.5 billion light years or more. All of the stuff that we see was actually compressed into a space smaller than an atom, a volume smaller than an atom. We don't have the physics that describes how that would work. That is so much mass, so much energy in so little volume. At this point, there wasn't even mass, just basically pure energy. That right now, our physics doesn't go there. As we get a better idea about how gravity works under very extreme circumstances, huge energy densities, we may have some idea what set off the Big Bang, and possibly what came before the Big Bang. And even that word is a little bit difficult when you start talking about the Big Bang, because the Big Bang, we believe, was the creation not just of space, but of time. Whatever state the universe was in before the Big Bang probably didn't have time as we perceive it either. Space and time appear to be some kind of a consequence of the later expansion. So how do you describe something that doesn't have space and time, that has huge amounts of energy in tiny little volumes? We don't have the physics. It's not that we will never know this, but right now we don't have any way to describe it. Now, another major misconception about the Big Bang is that the universe before the Big Bang was small. Okay, now didn't I just say that everything we see in the universe was probably contained, less than the volume of an atom? Didn't I just say that? Well, the thing is, I know every scientist understands that we cannot see the entire universe right now. And that's because there's such a thing that we quantify as the observable universe. The universe has existed, we think, since the Big Bang, about, say, 13.8 billion years. So as you look farther and farther out into space, you necessarily have to look back in time. If something is 1 million light years away from you, like the Andromeda Galaxy is about 2 million light years away, the light that you see through binoculars tonight as you look up at the Andromeda Galaxy left 2 million years ago. You're seeing the Andromeda Galaxy as it was. So today we actually have telescopes that are so powerful, they can see back to a time about 400,000 years after the Big Bang. That's amazing. We can see so far away in space that the light has taken that long to get to us, nearly 13.8 billion years. And when we look back to that time, the universe looks very different. For one thing, it's very hot. It's actually about as hot as the surface of the sun. And it's so dense and hot that we actually can't see any farther. Literally, in any direction you look around the sky, anywhere you look, if you look to that distance, you see the universe as it was at that time, 400,000 years after the Big Bang, and everything becomes just hot hydrogen gas. So I know this is kind of a strange way to put it, because we're talking about before the Big Bang, there may not have been space and time the way we think they are today. But whatever it was before the Big Bang, whatever was there was a tiny little part of it, a tiny little volume that expanded to become the universe we see today. But that little bit wasn't the whole universe. We don't know yet how big the original universe was, all of it, before the Big Bang happened, before something changed to make it expand and completely change its form. So the universe before the Big Bang didn't have to be necessarily tiny. It actually could be infinitely large. Because of that, we have no idea how big the universe is, what shape it has. All we can see is a tiny little bit of it. Think about my arm being the universe before the Big Bang, in some kind of state that we can't even describe through modern physics. The entire observable universe that we can see now used to be a tiny volume of it, maybe an atom in my arm. One atom expanded and became the entire observable universe that we see. But that's not the whole universe. There are trillions of atoms in my arm. Each one of those could expand to actually be its own entirely observable universe. So we can't tell yet how big the universe was before the Big Bang, or even what shape the universe is, because all we're seeing is a tiny little bit of it that expanded to become everything that we see. But that's not the whole universe. That's our observable universe. There's far more out there than what we can see. One of the most common questions that I'm getting from the public these days is our universe a simulation? I think that one of the things people are thinking about is they've heard the term the holographic universe. And this is indeed a very powerful and increasingly popular idea in modern physics. But it's a little bit unfortunately named. And let me sort of take you through this. This all started a couple decades ago when people like Stephen Hawking and others were trying to figure out how a black hole really works. We know black holes exist. We actually observe them from a distance very routinely. But the physics of how they work never quite worked. They appeared to violate some pretty important laws of physics. The universe doesn't like to lose information. A particle has a charge. It has a spin. There are all kinds of things you can say about an elementary particle. But when it falls into a black hole, the only thing that seems to exist anymore is mass, the gravity that particle had. What happened to the information about its charge? Can you ever get that back? As people began to do the mathematics of it, they noticed something very intriguing, that everything seemed to work much better if you assumed the black hole was two-dimensional. Now, black holes are actually three-dimensional objects. A lot of times they're portrayed kind of as things going down a drain, but basically you have a sphere, which is the point of no return. Gravity is so intense around a black hole that if you get anywhere this close, you never come back out. That's the event horizon of a black hole. So instead of assuming that it is a sphere around the black hole, it all started to act like it was a two-dimensional surface. Something that was three-dimensional became much more understandable if it was two-dimensional. And as scientists do, they thought, well, okay, if this works for a black hole, is it telling us something about the rest of the universe? And this may be one of the most important new revolutions in modern physics, that the laws of physics might work a lot better, might actually work out together, if you assume that our reality is really two-dimensional. You look around, there seems to be more than two dimensions in space, and there's time. How would that work? The example of a hologram came up. I still remember being at a hologram museum back in the 1980s, and the holograms were really new and really exciting. The idea that a hologram is made out of just a two-dimensional block of film or a block of glass, but it seems to be three-dimensional when you look into it. And even more than that, I remember this one hologram that was put on a pedestal, and as you walked around the hologram, somebody appeared to move inside and wave at you. If you were looking at the hologram, there appeared to be motion and even time, all embedded in just this two-dimensional surface. That's what they mean when they say holographic principle. It doesn't imply that anybody made a hologram, or that we are part of a projection that somebody, some evil genius, is projecting reality on us. What the holographic principle really is the universe may store energy in a way, and information in a way, similar to a hologram. If that's true, and we really are embedded in this two-dimensional universe, that has some pretty amazing repercussions. It probably means that every point in time exists at once. That, our idea that things are changing and that I'm moving right now and time is flowing in one direction, that's probably the same as somebody just walking by a hologram and having the perception that the image is moving. It's probably not real. The amazing idea is that the extension of space itself and time actually flowing may not be real, intrinsic parts of the universe. They may be some way that we perceive it with the human brain, but in fact there's an underlying reality where that is not true. We say that these are emergent properties. It's not the real story. A hologram doesn't really move. A hologram is not really three-dimensional. But it seems so through our perception. That's an amazing idea, that the entire universe exists all at once as some kind of surface of information. That's the holographic principle. It's working quite well right now. I can't tell you whether it's true or not, whether there really is some real two-dimensional thing that we think of as the universe. So stay tuned. At the time that Darwin was doing this, I think there was sort of this argument between like biblical people that said the Earth was a couple thousand years old, and then the scientists said, oh, no, it must be millions of years old. One of the things about being an astronomer is you throw around very, very large numbers all the time. I mean, some of them are just kind of, stupidly large, but even things like how many is a million, right? How many is a billion? The human brain, I don't perceive that really any better than anybody else. The human brain just doesn't go there. Instead, you kind of find yourself getting used to swimming in an environment where your mind can't really grasp all the way around a concept. It just can't. I can't tell you how far away a light year is. I mean, one light year, the distance light travels in 1 year at 186,000 miles per second. That's up close to about 6 trillion miles. I don't have the ability to actually visualize that or feel it. And yet, to me, a light year seems very familiar and actually quite close. So maybe that's one of the reasons astronomers are almost kind of predisposed to being able to let go of sort of your common sense. When people say things like the inside of a neutron star, is so dense that a single teaspoonful, of that material would have as much mass as Mount Everest. It's like, okay, the laws of physics pretty much require that. Or when people say, what was the temperature of the universe just, 3 seconds after the Big Bang, that our physics really does work to predict that. So I think that when you start swimming just in these big numbers and you begin to kind of let go of the idea that the human mind is the be-all and end-all, we have these tools to start attacking larger problems, to start asking bigger questions. All of a sudden it becomes very natural to say things like, oh yeah, gravity is actually a bending of space and time. The amazing thing about that is that started out to be completely theoretical. People thought that Einstein's theories were very useful. I mean, they made extremely accurate predictions about how the planets move, about how the universe works. But was there any really reality to the fact that space and time could bend? I mean, literally the space in front of me, the space and time around me can change and bend, even have a direction to it. It turns out that, our theories, for the most part, do lead us to something really physically true. And right now, people ask me questions like, are there multiple universes? What's the shape of the universe, the larger universe? All of these things are wonderful questions, and we don't know the answer to them yet. But I have a feeling that it's not just wasting time. I think some of these stranger theories will bear themselves out over time. We just need to wait. Right now, I think it's a little bit too soon to follow them all the way into the rabbit hole. Let's say that there were many, many multiple realities. Well, how would physics work? How would this work? It's still too much conjecture for me to invest a huge amount in it. I still remember, it's only 2,000 years ago and less that you had people like Aristotle who were brilliant. And they came up with this idea that all the planets had to follow perfect spherical orbits around the Earth in the middle, and they were on these crystal spheres that somehow moved. And people all the way up into the Renaissance were trying to figure out how those crystal spheres could have worked and how they were supported. Well, it turns out there weren't any crystal spheres. There's always a bit of me as an observational scientist that says, take everything with a grain of salt for now. Oh, I mean, Aristotle had this elegant, wonderful system. I mean, people loved it until the Renaissance, right? It's just that our observations didn't bear up with it. And it was so beautiful, people hated to let it go. But unfortunately, that's not how the solar system works. Definitely pursue these questions, but I'm not sure I'm ready to dive all the way into any of those rabbit holes quite yet. I love to think about them, but I think it's probably a little too soon to follow them ultimately to where they might go. So people today have all these wonderful questions that modern physics is leading us to. Questions like, are the way we perceive space and time real? That's even 100 years old. Albert Einstein said that space and time could be bent. Time itself could stop. Then there are things like the holographic principle. Is it possible that our whole universe is some sort of embedded information structure on a two-dimensional surface? These are amazing ideas, and they may turn out to actually have some physical truth to them. We're not really sure yet. But sometimes people say, well, are you scientists just absolutely crazy? How is it that you so blithely get rid of the idea that time has a direction or that space is real? One of the things you have to very deeply accept to be a scientist is that your senses, the human brain, is just not the best instrument to perceive the entirety of the universe. I mean, let's take a simple example. There are many, many colors of light, energies of light, that our eyes are not sensitive to. There are things like gamma rays and X-rays, ultraviolet light, radio waves. Those are all just different colors. that our eyes don't see. The universe has colors that just weren't built for the human body to perceive. And when it comes to a mind, a brain, think about some of the incredible creatures all around us. I mean, think about a grasshopper, a marvel of evolution. It has a brain, it has a central nervous system. But could you teach a grasshopper quantum mechanics or general relativity? Could it compose a symphony or write a novel? It just can't. I mean, a grasshopper's brain just doesn't have the complexity to do that. A grasshopper doesn't perceive those things. What about a bacterium? A bacterium doesn't even have a brain, but of course the majority of life on Earth by mass is still bacteria. You have to have this humility and remind yourself that it's possible that the human brain is just as far away from perceiving the way the universe really is as a grasshopper is to perceiving quantum mechanics. We are not some be-all and end-all of perception. The universe was not designed, not built, to be comprehensible to the human mind. We only see a little bit of it through the filter of what our minds can ingest and how they do it. And so we think that there really is such a thing as space and time. We actually think that there's a past, present, and a future, when in fact there may not be. And this goes all the way back to Galileo. When Galileo was around, the idea that the Earth had to be the center, God made it so. God must have put the Earth in the center. But then it became proven that the Earth went around a larger object, the sun. And I think almost more beautifully, one of my favorite observations of Galileo is that when he invented his little telescope, he looked at the sky and he realized that there were stars in the sky you couldn't see with just the unaided human eye. There were stars up there that we were unable to see unless you looked through a telescope, a piece of technology. And the question was, why would the universe do that if the universe was designed for us to see and us to perceive? Why would there be things too far away and too dim for us to see? Why are parts of the universe so strange and so incomprehensible and make so little common sense? Honestly, why should it be any other way?
Want to support the channel? Join the Big Think members community where you get access to videos early, ad-free.